question 7 in this paper is really quite a demanding question, I think. And some of you will have struggled to get 4 marks here, probably quite a lot of you. You really have to understand, though, that the bonding topic is probably the most important topic of chemistry, and the one where if you're going to score a good grade or the best grade you can, you have to get your head around this bonding topic as best you possibly can. To answer a question like this one, you've got to think, well, what type of bonding has the substance got? The substance we've got to talk about is cesium oxide. Now, you have probably never heard of or been taught about cesium oxide, and they will do this to you in the exam. They will ask you to describe the bonding of something you've probably never seen before, but you have to use the knowledge that you've got. So the first thing to do is recognise that cesium, find it on the periodic table. You're told it's in group 1, so you know cesium is a metal. And I'm going to just remind you the word metal has got a plus in the middle of the word conveniently. And oxygen is a non-metal. I'm sure you all know that, but oxygen's a non-metal in group 6. So just going to make a note of that up there. So this is group 1, and it's oxygen's a non-metal. Conveniently, the word non-metal has got a minus right in the middle of the word. So this is in group 6 of the periodic table. In other words, the 6th column, first column and 6th column. If you've got a metal and non-metal, you have to know that without exception, every time you have a metal and a non-metal compound, it's going to be what we call giant ionic. And you've got to be able to describe how giant ionic compounds form from their elements. So we've got a cesium atom, which has got 1 electron in its outer shell because it's group 1. We've got an oxygen atom, which has got 6 electrons in its outer shell because it's in group 6. So when an ionic compound forms, what happens is that there's a transfer of an electron from the metal to the non-metal. That's really all that goes on. That's the most important bit of it. So cesium's got 1 electron in the outer shell, and when compounds form, you always end up with full outer shells. And cesium loses 1 electron, the one it's got in its outer shell, in order to get a full outer shell, you could say, and that leaves it with a 1+ charge, hence the plus written there. So cesium, just going to write it as Cs because that's the middle of the periodic table, loses 1 electron to form what we call an ion, a positive ion. And it does that in order to end up with, you could say, to end up with a full outer shell. One that wasn't in its outer shell is now gone. And where that electron goes is it goes to an oxygen atom. But oxygen's got 6 in its outer shell because it's in group 6. And in order to end up with an outer shell, it needs 8 electrons. So it must be that this process happens twice from 2 different cesium atoms. So one cesium loses 1 electron, another cesium also loses an electron, and both of those electrons end up at oxygen. But in the end, oxygen gains 2 electrons. Again, we end up with a full outer shell. And we've gained 2 negatively charged electrons, and so oxide, we now call it, that's formed has got a 2- charge, and again, we've ended up with a full outer shell. And some people definitely struggle to remember whether it's a minus or a plus ion in each case, but just remember that cesium's got a plus in the middle of the word because it's a metal, and a non-metal has got a minus in the middle of the word. Right. So you've then got to get the next, that's worth a mark by the way, as is that. To get the 3rd mark, you have to be clear this idea that this top process must happen twice. So you'd say 2 cesium atoms each lose 1 electron to get the extra mark there. Or you could say this process happens twice. And then what you end up with is a cesium plus ion, an oxide 2 ion, and I think that gets you the final mark for having those things. Just checking the mark scheme here. But you should be, I would say, although it doesn't appear to be in the mark scheme, but you should be clear that in the end you've got 2 cesiums and 1 oxide in the compound cesium oxide. And that's another way of getting that second mark, that third mark, by the way. Okay, so that's the way you've got to go about tackling that question. Make sure when you're practicing and preparing for your exams next year that you're really confident describing how covalent substances form and ionic substances form and metallic substances form. This is a much more standard question and should have been easy if you're well prepared. The tricky thing for you though might have been again that it's cesium, which you may not have discussed. But cesium, as we've said already, is in group 1, and all you've got to do is explain why cesium is more reactive than sodium, which is the same as explaining why potassium is more reactive than sodium. It's exactly the same argument. So the way that you would explain that is, well, I'm going to, just to make it easy, just to remind you of the chemistry, I'm going to compare lithium, which is in group 1 as well, which you'd have been taught, and I'm going to compare that with sodium. And then we're going to make the same argument for the exam question. So I'm just going to do a little bit of a reminder. Stuff you did way back early in year 10 and maybe you've forgotten. So they're both in group 1, both got 1 in the outer shell, but the difference is that sodium's got one more electron shell, in other words, one more shell between the outer electron and the positive nucleus of sodium. Now when group 1 elements react, they react, as we've said already, by losing 1 electron. And the easier the atom loses the electron, the faster it reacts. And so sodium loses its electron more easily, more quickly than sodium, and so it reacts faster. And we see that when we chuck it into water, it kind of fizzes and moves around really quickly and disappears quite quickly. And cesium does it so quickly, it does it explosively. Now why is that? That's simply because that electron is further from, or one of the reasons is that electron is further from the nucleus. Nucleuses, or nuclei, are positively charged, and electrons are negatively charged, so they're held together by a force of attraction that we call electrostatic attraction. The weaker that attraction, the easier it falls off. And the further away they are from each other, the easier they fall off. And that's what you've got to say. So you'd say, if we're then comparing cesium, I'm not going to draw this because it's got loads of shells. It's got 1, 2, 3, 4, 5, it's got 6 shells, so I can't be able to draw it. But all you've got to say is that cesium has more shells. So you're just stating what you can see in the periodic table. You don't even have to explain it that well. So cesium has more shells. You might call them energy levels, but probably shells is what you've been taught. And that means for a second mark, it's really important you refer to the outer electron now, the one that's lost. The outer electron is further from the nucleus. And that means, as I've said already, there's a weaker attraction. To the nucleus, and you might, to make it slightly more shiny, slightly more perfect answer, say weaker electrostatic attraction to the nucleus. But then for the fourth mark you've got to say, so it's lost more easily. So electron, lost more easily. And that is an absolutely routine standard 4 banker marks in your paper 1 next year, I would say. So 4 mark, boom, 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 boom. That's one of those ones that you would just learn and practice, but you can practice with lithium and sodium and get your head around it. You might have talked about shielding as well, and if you have, that's lovely, but you don't need to talk about shielding to get the mark, so I'm not going to go there. Right, 7.3 shows a bit of the early periodic table that Mendeleev put together. It didn't look like this, but they've made it look like that to make it easy for you to see what's going on. Now this is different from the normal periodic table that we're used to, the modern periodic table, because tellurium, Te, and iodine, oh no, they're the right way around. What's going on there? I'm just going to pause the video and have a little look. Yeah, sorry, I didn't read the question before starting working on it. This is the periodic table we're used to seeing, with you've got the group 6 elements here, group 7 elements here. In the original periodic table that Mendeleev put together, he had tellurium and iodine the other way around. Okay, so he had them that way round. Why did he do that? And the answer is, we'll just look at the numbers at the top here. These are what we now call the mass numbers. And look, 128 bigger than 127. So he had them the other way around, based on their what we call atomic weights. And you really should be saying atomic weights because that's the word that Mendeleev was using. which is equivalent to, or roughly equivalent to, what we now say is atomic number. Atomic mass. So what you need to say for the marks here is elements were sorted in Mendeleev's day by atomic weight, and that's worth a mark. And then say that iodine has a lower weight, atomic weight, than tellurium. And so he had a bit of a problem to deal with. But what Mendeleev did, what made him the genius that we still talk about all these years later, is that he recognized, well, maybe there's some sort of issue here that they didn't understand back then. And he recognized that it was more important that iodine should be with elements that it's really similar to. Iodine is really similar to bromine, which is quite similar to chlorine, which is quite similar to fluorine. Tellurium is really similar to selenium, which is similar in lots of ways to sulfur and then oxygen. And so what he did was he grouped elements, instead of worrying about too much about the atomic weight, which he thought they'd got wrong. He thought they'd measured it wrong, in fact. He put the elements, so he grouped elements with other similar elements, or grouped elements with other similar elements, or elements with similar properties. Something like that. The mark scheme says he put iodine with elements with the same or similar properties, or you could also say he put tellurium with elements of the same or similar properties, or you could have said, that's it really. That's what you've got to say there. So I'll pause this video and I'll start another video for the next question.